Okay, hello all, and good morning. Welcome to our fifth lecture for neural networks and deep learning for this academic semester. So actually, this is going to be the very first lecture that we will be talking about neural networks. However, I hope that by this time we have already become familiar with the so-called deep learning pipeline, which consists of the following steps. So first step is dataset, data loader. Okay. So the first step is to create the dataset and the data loaders. The second step is to create and initialize the model. Okay. The third step is to create the loss and the optimizer. And then the final, the next step is to create the training function. And then the last step is to train and evaluate the model. Okay. Train and eval. So although it's our very first lecture on neural networks, we should be already to some extent familiar with this pipeline. It's the same pipeline that we use for linear regression, for softmax regression, and we will be using exactly the same pipeline for today's lecture, which is on multi-layer perceptrons. The only thing actually that we will be changing is the model. So everything else will stay the same, okay? So in the first hour of today's lecture, we will be talking about this kind of model, new model, okay? Multi-layer perceptron. And then in the second hour, we will discuss important parameters for training MLPs. So training of MLPs is a little bit more tricky than training linear models, okay? So first of all, why do we need linear models? So in a linear model, if you remember, the output is a linear combination of the input, okay? So W1 times X1 plus W2 times X2 plus WD times XD plus this bias. So the output is a linear combination of the input X1, X2, XD. So that's why it's called a linear model. But in many cases, the output, okay, cannot be expressed like this, okay? And if we do that, so if we do use a linear model, this eventually will result a very weak model. A weak model means that, you know, we will not be able to get very good predictions, okay? So our predictions, let's say y hat, and the real data, the real labels, and the real labels y would not be very close, okay? So here we can see a very simple example. So the probability of loan repayment, okay, is not linearly related with income, okay? What does it mean in practice? So an increase in income, okay, from 0 to 50K, £1,000, let's say, results in a much bigger increase in the likelihood of repaying the loan compared to an increase from 1 million to 1.05 million. So the increase, okay, is the same, okay, is 50K, okay, for both cases, for both this case and this case, okay. But then the probability of repaying the loan hugely increases when you are in this case over here, right? So if you're already making $1 million, the probability of repaying the loan is like 100%, right? So you already have a lot of money. So this same increase doesn't really change the probability for this case, okay? But it increases the probability by a lot for this case, okay? So many times the output of a model, in this case, the probability of repaying a loan is not linearly related to the input feature, which is the income in this case, okay? So what can we do to fix this, okay? How can we go beyond linear models? So the first thing that people have tried for a long time, and also this is something that is still heavily used, for example, is used quite a lot in medical applications, is called feature extraction. Okay, so feature extraction means that the input data is somehow preprocessed. So instead of using the raw input data, we use some features derived from this data, okay? So for example, we can use the logarithm of income as our feature. So instead of using income, we use the log of income. Okay, that's an example. A second example is from, I can think of is from last week's lecture, where, for example, if you remember, we had this tiny 2x2 image, okay? And then we said that to describe this image, we take the pixel values, x1, x2, x3, x4, and we create a vector x2, x3, x4, okay? So last week we used directly the pixel values, okay? x1, x2, x3, x4. Now, what I can do is that I can extract features from these values and then use the features as input to my softmax regression model. So for example, I might use a feature f1, which is the mean value of x, right? Which is x1 plus x2 plus x3 plus x4 over 4, okay? Or then I can use like another feature could be the standard deviation, okay, of x. So the standard deviation shows the spread of the values around the mean value. Then another feature could be a difference, and this is heavily used in image processing. So you may want to take the difference x1 minus x2. Then f4 could be, for example, x2 minus x3. f5 could be x4 minus x5. Actually, you can have a very long number of features. So f1, f2, f5, and you can carry on, calculating different types of features from the original pixel values. Okay, so you can have like loads of these features, let's say. So the input, so the feature vector doesn't have to be the same size as the original input. Okay, and then once you have created this new feature vector over here, then you're using this guy instead of this guy. Okay, so this is what you use as input to your softmax regression classifier. Okay, so now obviously there is a huge number of ways for defining these features, and this is called the process of defining these features is called feature engineering. Okay, and this feature engineering kind of depends on the actual domain. So maybe you have different ways to extract features from images than from audio, or from, I don't know, some other modality, from language, for example. Okay, from text. So it requires some domain expertise to require features that have some meaning. Okay, and usually an expert decides what features to choose. Okay, for different domains or problems, and this process is like very tedious. Okay, so before neural networks, this was something that people were doing a lot, and loads of people were trying to find the best features for each domain. And yeah, so this was called feature engineering, and it's something that we don't have to do with deep learning. Okay. What is the definition of a feature? A feature is something that you can calculate using the original input data. Okay, any combination of these. So originally we have the pixel values, right? So you can say that we're using as feature the pixel values, which are like the raw data. Any function, any combination that you can come up with from this input data is called a feature. So particularly, handpicking features has been a very poor choice for solving difficult computer vision problems like object recognition. And that's why deep learning and neural networks are very important for this area, the area of computer vision. So for our fashion MNIST data set that we used last week, actually we saw that using pixel values works pretty well. Okay, but that's an easy data set. Okay, it's not very difficult. However, for very difficult data sets like the ImageNet data set, where our training set has like 1 million images, and we have in total 1,000 classes, and these are like real world images. They're not just some clothes kind of put in a black background as a fashion MNIST data set, right? If you try to handcraft features, like define your own features and then train a model for classification, then you get very low accuracy. Okay. So what we will do from now on is to use deep neural networks for two things. Okay, so one is to learn how to extract features. So that's task one, learn how to extract features. And then task two is to do the classification. Okay, so how does this work in practice? It works as follows. We're gonna use exactly the same method for classification as we used for last lecture. So the very last layer in a neural network is a softmax regression layer. Okay. So that's the very last layer of a neural network. It's exactly the same as what we saw in last week's lecture. Now the difference is that the input to this layer, okay, is not the raw data. Okay, so if you remember here, we had as input the x, right? So here we were using as input x. So x1, x2, x3, x4. So these were like the raw data. So it's not going to be that, but it's going to be the output of another layer. And the output of this guy will be some sort of feature vector, okay? And then we can have as many features as we want. But these features that we have here, so this layer will have some training parameters, and these features over here will be produced by these training parameters. So we will learn how to extract the features, okay? We will not manually define this kind of handcrafted combinations that we saw previously. So the features will be learned, and the features will be that we will learn will be used as input to the softmax regression layer that is the classifier, okay? Classifier. And then after the classifier, you get the prediction, okay? And actually, what will happen is that we can have not just one layer to extract features, but we can have as many layers as we want, okay? So all of these guys put together will be used to extract the feature at this point, okay? The feature that goes to the classifier. And then we use softmax regression. Does this make sense? Yes, no? Anything that is not clear? No, feature extraction works not only for classification, but also for regression. Okay. Let's see like an example of this. So as just mentioned in the previous slide, like a neural network consists of stacking many layers on top of each other, okay? So have 1, 2, 3 layers, one after the other. And then if each of these guys over here, so this guy, so this guy, this guy, this guy, all of these guys are fully connected layers, then the architecture is called multilinear perceptron. Okay. So what is a fully connected layer? Do you remember? So a fully connected layer, if you remember, it's very simple. So this is the output of the layer. This is the input of the layer. Okay. So each output is connected with all inputs. Okay, so this guy is connected with all inputs. This guy is connected with all inputs. Okay. So that's a fully connected layer. How do we mathematically define a fully connected layer? You remember? Linear function, yes. Something more specific? So if X is my input vector, sorry, if X is my is a batch of input data, okay, so it's like a matrix, okay, n times 4, so n examples in my batch, 4 features for each example, so this is X. How do I get the output in a fully connected layer? So it's a matrix multiplication. Okay, so I multiply X with W, and then I get the output, let's say O. Okay, O equals X times W. Okay, and so if W has dimensions 4 times 8, what will I get as an output here? What will be the dimensions of O? N times 8. So it would be a matrix. Okay. So it will be a matrix like X. It will have the same number of rows, N. N is the number of examples in my batch. But now each example will be represented by 8 features. So there will be 8 elements, okay, in each row. So here, okay, so here in X, each example is represented by 4 features, where here in O, each example is represented by 8 features. And to achieve this, I take X, I multiply it with a matrix W, which has dimensions 4 times 8. Okay, so 4 is the number of input feature dimension, and 8 is the dimension of the output feature. Okay, and then that's how I get O. That's a fully connected layer. Okay, so here in this example, how many fully connected layers do I have? Well, I have 2. Okay, so I start from 4 features, then I go to 5 features, okay, and then finally I go to 3 outputs or features. So I from 4 I go to 5, and then from 5 I go to 3. So I would be using one. So the first weight matrix will have dimensions 4 times 5, and then the second matrix will have dimensions 5 times 3. Okay, and you see here that this is my first layer over here. So this will be using weights W1, and from 4 inputs I go to 5 outputs. Okay, so this is the output of the first layer, and then the output of the first layer, which is this one, is serving as input to the second layer, which is this layer over here. And this layer will be using a different weight matrix. Okay, so this is an example where I have a 2-layer MLP. Okay, now I have a 2-layer MLP. However, this layer is the output layer. Okay, so actually, so it's like my so this O1, O2, O3 are the outputs that I'm using to, let's say, predict three classes. Okay, so this is the kind of example that we saw in the last lecture, right? So we were interested in predicting the three classes: dog, rooster, and horse, I believe. So three classes, right? So actually, this layer over here, okay, is my softmax regression layer. Okay. Okay. So this layer over here is the softmax regression layer, and then my network has one more layer, which is this layer over here, for learning how to extract features. Okay, so I have one layer, which is this layer over here, that is used to extract some features from the input data, and then these features are fed as input to my softmax regression layer to do the classification. Does make sense? Yes. But as said, we can have multiple layers. So in this example, I have only one layer to extract features, but you can have multiple layers. Okay. Here I have only one layer to extract features. Okay. Okay. Yes. A softmax regression is a fully connected layer. Softmax regression is a classifier, and it uses a fully connected layer. Yes. Hidden layer is the layer that is used to extract features from some input features. Okay. In the very beginning, we will have the raw data. Okay. Any other questions, guys? Okay. Let's move on. So in this example over here, okay, in this two layer MLP, what happens is that from X, we have X, so this is n times 4, okay. Then we go to this layer over this guy over here. Okay. So what will be the dimensions of that guy? Can you tell me? So from X, which is the data matrix, the design matrix, I go to this intermediate representation, okay, which is going to be a matrix. Okay, I will call it, so this is X. And let's say this is H. What will be the dimensions of this matrix H based on this figure? So the input is n times 4, and based on this figure, what will be the dimensions of H? N times 5, 4 times 8, n times 5, n times 5. Are we converging to some solution? 4 times 5. So the right answer is n times 5. So always H will have as many rows as X. So if we are processing n examples, okay, then we must get n examples. So if the input to any layer has n examples, then the output of this layer must also have n examples, right? So H will be a matrix, will have as many rows as X, okay? So it will have n rows. The only difference is that X, for each row, it has 4 features, whereas H, for each row, has 5 features, okay? And how do we know this number 5? We know here because we have 1, 2, 3, 4, 5 features, right? Whereas in the input, I have 1, 2, 3, 4 features, okay? So H will be a matrix of dimensions n times 5. And then I pass this H to the second layer, and I get O. So what would be the dimensions of O? Based on this figure? Exactly. It will be n times 3. Again, I will have as many rows as the input, n examples, but now I have 3 output features, okay? And then the output can be passed through a softmax layer and then get my final output, okay? So this transition over here from X to H is described by this equation over here, okay? So I have ignored the biases all this time, but to simplify things, okay? I can always add something to the result, which is this bias, but it is not so important to understand how this works, right? So let's ignore the biases, okay? So, or let's assume that the biases are 0, right? So this transition from X to H is described by this equation. And as we said, in this case, W will have, what will be the dimensions of W? It will be times 4 times 5, okay? 4 is the input feature dimension, 5 is the output feature dimension. So this is the first matrix, W1, okay? And then the second transition from H to O, which you see over here, is described by this equation over here. And transition is done using this W2 matrix, which has, so W2 will have dimensions 5 times 3, okay? So these are also the maths of the model, okay? Question, is this process clear? How we go from X to H and from H to O, including the dimensions of the matrices, okay? Is this clear? Perfect. That's great. And as I said, you can have actually lots of these intermediate layers. So you can have from X to go to H1, then from H1 to go to H2, to, you know, H3, whatever, and then you go to the output, okay? So you can have many of these intermediate layers. So in this case, we just had one, okay? Of course, very good question. Can the hidden layers change in dimension? So you can do whatever you want. So in this example, from 4, we went to 5, and then we went to 3. So 3 is the number of output classes, right? But you can go from 4 to 10, then you can stay, you can use 10, then you can reduce it to 8, then you can reduce it to, you know, 5. You can, or you can go, you can do whatever you want. Okay. You define, this defines actually the architecture for your MLP, right? The number of these dimensions over here. This is something that we define, okay? Normally, the rule is that we try to go to a higher hidden dimension, okay? And then we reduce it as we go close to the end. That was a good question. So we have this model over here, okay? I will clear this annotation. So we have this model over here described by these two equations. And my question to you is there any problem with this model? What do you think? We have this 2-layer MLP that is described by these two equations, right? So is there a problem with this model? So the problem might not always want to move sequentially through layers. What do we do not know what is happening in the hidden layer. I'm afraid that these are not the right answers. Now, it's a little bit a tricky question. So actually, we can show that this model over here is still a linear model. Although we have 2 layers, okay, each layer is kind of described by matrix multiplication, okay. Now one can define a single layer, okay, a single layer linear model, okay. So a linear model with 1 layer, okay, where the weights are given by this relation and the biases is given by this relation. So what I'm trying to say is that this model over here, okay, is still linear model, okay. Although we have 2 layers, actually you can put as many layers as you want, okay. Still, if we stack many linear layers on top of each other, what we get is still a linear model. And for this particular example, this linear model, which is a single layer model, can be defined using these weights over here and this bias. So I can have a new model that goes directly to the output, and then here I would use W1 times W2, okay. So if I define W to be W1 times W2, I can use a single layer linear model, okay? So if this is still a linear model, then by just stacking linear layers on top of each other, I didn't really achieve anything, because in the end, I'm still having a linear model. Okay, is this clear what the problem is? Not exactly. So our goal was to go beyond linear models. Okay, this was our goal, because a linear relationship is not a very powerful relationship to relate the output with the input. Okay, so to avoid doing that, we introduced a two-layer architecture, which is the architecture over here. Okay, so this architecture is a two-layer architecture where each layer is a fully connected layer, or a layer that is described by a matrix multiplication. So this two-layer architecture over here, as it is described by these two matrix multiplications. Okay, but what can show is that we don't really gain anything if we do that. Why? Because I can define a single layer architecture, which where the weights are given by this relation over here. Okay, so I can define a standard linear model with these weights over here. So the weights is the multiplication of W1 and W2. That can produce exactly the same outcome. Okay, so in the end, this model over here, reduces to a linear model. Okay, so although it's a two-layer architecture, it can still be expressed as a linear model. So I didn't really gain anything. Okay, and you can prove actually this, but okay, if you want, you can have a look at the proof. Okay, does it now make more sense? So we have to do something extra, okay, to go away from this linear model. Okay, exactly. So, and the same applies as more layer. So it doesn't really change anything. If we stack 10 fully connected layers, one after the other, one on top of the other, it will still be the same. Okay, still. So actually, if you like stack 10 layers, it would be that your final, the equivalent weight matrix will be given by the product of all these matrices. Okay, so this result can generalize to as many layers as you want. So to be able to go beyond the linear model, we have to introduce another component, okay, to our MLPs. Okay, by just doing that is not really enough. Okay, so to realize the full potential, okay, the full potential of MLPs, multi-layer architectures, so we need one more key ingredient, and that ingredient is called non-linear activation function, sigma. Okay, and that function is applied to each hidden unit after the linear transformation. So it's very simple. Okay, So previously we had H, if you remember, was equal to X times W, okay, plus the bias, but let's say ignore the bias. Now what we will have is that H is equal sigma. So we first compute X times W, okay, and then we apply this sigma function that you see over here. So, and this sigma function is a nonlinear function, okay, and it's applied element wise, okay. So from X matrix I go to this H matrix over here, okay. So this would be n times 5 from my previous example. So, and then I have this sigma function. Each element, this function sigma, is applied to each element of the H matrix, okay? That's the only difference. I calculate H matrix and then apply on each element this sigma function, okay? Activation function, okay? Does it make sense? That's the only difference, basically. Now, here, how many times do I have to apply this nonlinear function? Let's clarify this, okay? So the last layer, this layer here is the softmax regression layer, okay? So I will not apply the sigma function to the output, because in the softmax regression layer, the output is kind of processed by the softmax nonlinearity, right? So we saw that in the previous lecture. So this sigma function that you see over here is applied to the output of each hidden layer, okay? So if I have X, then I take H1, then I take H2, then I take H3, then, you know, H10, then O. So this sigma function over here, okay, is applied to this guy, then to this guy, then to this guy, and so on, okay. But I do not apply sigma on the output, because the output is already made nonlinear by using the softmax function. If I have, this is for classification, if I have regression, I don't apply anything, okay? But that's the only difference, that I basically apply this function element-wise to these matrices, to this hidden kind of matrices, H, okay? Normally, you use the same activation function for all layers. There is a case that this can change. I will discuss this later, but you know, mostly you're using the same activation function. Does it make sense? That's the only thing that I have to change. Now I have an MLP, okay? So this is actually an MLP. The previous one was a linear model, okay? Any questions? The activation function is handcrafted. I have to choose it. And yes, it will do something on the input features. So it will do some sort of nonlinear processing. But this is beneficial, okay? So I can't really say that it ruins the data, because if I add it, I will be able to train a more powerful model. Okay. Now, something a little like a theoretical result. Okay, it's not like we will not go into the theory, but the theoretical result is the following. In all previous lectures, our models were linear models, and that means that they can learn nonlinear relationships between the input and the output. Okay, and as we said, we want to introduce these MLPs to go beyond modeling linear relationships. Okay, now one can show that an MLP with just one single hidden layer, okay, just one. So like this guy over here, right? This guy is an MLP with a single hidden layer, okay? So an MLP with a single hidden layer, and sufficient and arbitrary but finite number of neurons. So this is the number of neurons, okay? Okay, the number of the features in the hidden layer, okay? So, so what I'm saying is that, this number is finite, okay? It could be 10, 20, 100. So there is like a finite number. So an MLP with a finite number of hidden neurons, okay, can approximate any continuous function, okay, any function, to reasonable accuracy under some certain conditions for the activations function, okay? So actually with a single layer MLP, okay, so XHO, okay, we can approximate any function f, okay? Whereas with a linear model, we could only approximate a linear function. A single layer MLP suffices to approximate any function, okay? Any crazy function that you can think of, continuous, can be approximated by MLP to some sort of, very good accuracy, okay? Now, there is a caveat with this theoretical result, and the caveat is that we need to know the weights. So for this like single layer MLP, if we know the weights, what would be the values of the weights, then we can approximate any function, okay? But the problem is that our training algorithm, which is SGD, is not powerful enough to find the weights for single layer MLP, okay? So it's very difficult to define an algorithm to find the weights of single layer MLP to approximate any function, okay? So although this is it sounds very nice from a theoretical perspective, it's not very practical because I don't have a weight to find these optimal weights. However, if instead of using a single layer MLP, I use a multi-layer MLP with several layers. So H1, H2, H3, H4, O, that's the output. Then SGD is powerful enough to find the weights, okay? So for each layer, I will have a weight matrix W1, W2, W3, and so on. Now, in this case, SGD is powerful enough to find the weights. And that's a reason that people are using deep neural networks and not just single layer neural networks in practice, okay? That's why deep learning has been so powerful and so popular, okay? Now, from a more practical perspective, let's have a look to see how this activation function looks like. So nowadays, the most widely activation function is the rectified linear unit, also called ReLU, okay? And this is the output of the ReLU. And actually, this function is very simple. If X, if the input is less than 0, then make the output 0. If X is greater than 0, then just keep the number as it is, okay? So the output is X, okay? So that's this function ReLU. If X is less than 0, okay, then make the output 0, okay? So, if X is greater than 0, then keep the value, okay? So if my feature, okay, so let's say that we have this H matrix, okay? So it has dimensions n times 5. I take the first row, okay? Then first row is minus 0.1, minus 0.2, 3, 4, 5. Then if I pass this through a ReLU, then I will get 0, 0, 3, 4, 5. Okay, first element, second element, third element, fourth element, fifth element. Okay. Is that okay? This is the most popular activation function, sigma. Okay. So this function that you see here is called piecewise linear. So from minus infinity to 0 is linear. From 0 to plus infinity is also linear, but they are connected at 0. So it's called a piecewise linear function. So put together, a piecewise linear function is a nonlinear function. Okay. Yes, this is a mathematical kind of way to define the function, right? Also, maybe you want to avoid using if statements when you code this. Okay. Is this clear what the ReLU function does? Perfect. It's pretty simple, actually. Now, this is the ReLU function. And what I want to show you here is actually the derivative of the ReLU function, okay? Okay. This is the derivative of the ReLU function, okay? So first of all, the ReLU function is not differentiable at x equals 0 because that's the point of nonlinearity. But for x equals 0, we just set the derivative equal to 0, right? So we can set this by hand. Okay. Now the derivative for x greater than 0 is this line over here. So as you may see, is 1. okay? So for all input values that are greater than 0, the derivative is 1, okay? And so this makes the optimization, the training procedure, to be well behaved. This is the actual favorable feature of using the ReLU. And then when x is less than 0, then the derivative is basically 0, okay? Okay, so why is this important? Because we are introducing this nonlinear function in our formulation, this sigma over here, okay? This sigma over here. And we don't really want this sigma to cause problems when we calculate the gradients, okay? And this function doesn't cause any problems because the gradients are all the same and equal to 1, okay? Now, there is another, can you see a problem with the ReLU function? So this is the ReLU function. Can you see a problem with the ReLU function? Well, the problem with the ReLU function is not a huge problem, okay? But the problem is that all values that are less than 0, okay? So all values that are less than 0 are mapped to the same value, which is 0. So you see here minus 0.1 and minus 0.2. I mean, you could have a different value, minus 0.9. All values are mapped to 0. So this results in some sort of information loss, okay? So actually, there is another version of the ReLU that doesn't set the values to 0. So maybe there is a small, tiny slope here. Okay. So it looks like this. So the negative values are not mapped to 0. Okay. Still, this function is a piecewise linear function, and it's non-differentiable at x equals 0. So this function is called ReLU. Okay. ReLU. Okay. So we have like two slopes, one for the positive values and one for the negative values. So this is the slope for the negative value. And yes, ReLU is similar to leaky ReLU. Now the slope of that corresponds to the negative values in leaky ReLU must be provided. So you just say that I want my slope to be has some value, very small, but in ReLU actually you can learn this, the slope. So the slope is learned, and if you have a ReLU for each layer, then the slope will be, so this, you make the slope a network parameter, and you can learn this with SGD. And if you are using a ReLU for every layer in your network, then different values will be learned. So you will have like different types of activation functions, okay? So, and that kind of answers this question that was brought up earlier, whether we can use a different activation per layer. If we use, for example, a ReLU where it has this slope over here and this slope is learned, then you will end up learning different slopes for different layers of the network. Okay. Okay, well, a max is calculating the max between two values, x and 0, right? So if x is greater than 0, then max returns x. If x is less than 0, then max returns 0. Take the max between the two arguments. Yeah. Okay. Now, before using ReLU, people were trying to include in MLPs another function, another activation function, which is called the sigmoid function. Okay, so for many, many years, people were trying to optimize MLPs using the sigmoid-based activation function. And why they were doing that is basically because in biological neurons, okay, the activation function is like a step function. Okay, so in biology, this is the activation function in biological neurons looks like this. Okay, is the step function. But the step function is a non-differentiable, so people came up with this function over here. Okay, so this is the step function. Okay, and this is the sigmoid function, which is given by this formula. So basically, you can see that the sigmoid function squashes everything between 0 and 1. Okay. So this function, in contrast to the step function, is smooth, differentiable, has some nice properties. However, there is a problem with the sigmoid. Sigmoid doesn't work well. Okay, and that was one of the reasons that people were not able to get they were not able to train neural networks in the past. Okay, now the reason is that this is the derivative of the sigmoid. Okay, so what's the problem with that? The problem with that is that as we get away from 0, the derivative of the sigmoid becomes very small. Okay, so what does this mean? It means that the gradients, when we calculate the gradients that are passed through the sigmoid function can become very small. Okay, so after introducing the sigmoid function, the gradients might become very small. And this phenomenon is also exacerbated if you have many layers in your network. Okay, so the first layer will make the gradient small, then the second layer will make them even smaller, and in the end you will get very low gradients. So if the gradients are very small, then you don't learn anything. Okay, so it's very difficult to train neural networks using the sigmoid function for this reason. Okay, so that's why people discovered ReLU as an alternative. But in terms of like motivation, sigmoid function seems more natural fit because it kind of approximates more naturally the step function, which is used in biological neurons. And then another function that is very similar to the sigmoid is the tan H function. So it's similar also in the shape. So you see the shape is similar. So this is the sigmoid. The difference with the tan H is that it squashes everything from -1. So from -1 okay, to 1. So the sigmoid squashes things from 0 to 1, and tan H squashes things from -1 to 1. Again, tan H function. So also this is a function that was used in neural networks a long time ago, especially in recurrent neural networks, but it has the same problems so as the sigmoid. Okay, so the activation of choice for training neural networks nowadays is the ReLU function. Okay, any questions? And I think with that we can finish the first hour of today's lecture. Questions? If you have no question, well, let's make a break. Think about if you have questions. You can always ask in the chat and I'll try to answer them as quickly as possible. Let's do a break and I will be back in 10 minutes, like 10:30 we can start again, okay? Hello. Sorry for the slight delay. So we can start for the second hour of today's lecture. There are a couple of questions before we actually start. So the last layer in an MLP is a classifier if you are solving classification problems. Okay, like a softmax regression layer. Softmax regression layer is a linear layer where the output is processed by a softmax. So a softmax is a non-linear function. Okay. So that's the only thing that you need to know. Okay. But if we're solving a regression problem, then the last layer is not a softmax regression layer, is a linear regression layer. So in that case, the very last layer is a linear layer, okay? But some people also, when they refer to the softmax regression layer, they kind of, you know, they call it a linear layer, like a classifier, okay? So they don't really consider the softmax when they define it, like, so in terms, it's a kind of a terminology, okay? Now, so softmax function is, no, softmax function is not, is a nonlinear function, but is not used as an activation function. Softmax function is used to normalize the outputs of the linear layer to make them probabilities. And this has specific use, okay? So for the hidden layers, we're using ReLU, and for the very last layer, we're using, for classification problems, the softmax function to turn the outputs into probabilities for the reasons that we explained in the previous lecture. Okay. Okay, so maybe we can start for the second hour of today's lecture. So in the previous hour, we talked about the theory of MLPs. And as we said that optimizing training MLPs is a bit trickier than optimizing, let's say, linear models like linear regression or softmax regression model. So in this hour, we will discuss important training options and hyperparameters that are related to the effective training of MLPs. And when we say effective, basically, I mean two things, okay? So, and we have discussed two things, when, okay? So one is, the first thing is to minimize the training loss. Okay. So what does this mean? It means that the model can fit the training data. Okay. So if we minimize the training loss, it means that we can make more and more accurate predictions for our training data. Okay. So minimizing the training loss means that the training accuracy will also increase. Okay. Or equivalently, the training error. Okay. So the error, so the accuracy is 1 minus the error, okay? So if we minimize the training loss, the accuracy will increase, the error will decrease, as you may see over here, the training error. Okay, so as we keep training, the error goes down. So the model fits better the data. However, that's desirable, but it's not our ultimate objective. Why? Because what we really want from the model is to generalize well to new data. Okay, what does it mean? It means that once we train the model, we want to take the model and apply it to some new unseen data that were not used for training, and then check the model's accuracy on that new data. Okay, so what we care is the accuracy on separate, okay, validation slash testing set. Okay, so both these things are important when we train a model, but the really important is the second, which is the model able to generalize to unseen validation or testing set that was not used for training the model. Training the model means finding the model parameters. Okay, so actually from this example that you see over here, it looks like the validation error. So as we train, it goes down, 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 and so at some point after this point over here, so after the 30th epoch, it starts going up. Okay. So what does this mean? It means that after training for 30 epochs, the model starts overfitting. Overfitting means that the training error goes down, but the validation error goes up. Okay, so this is a kind of sign of overfitting, and that's something that we want to avoid. Okay, does this make sense? Okay, so now, how effective is the training procedure in terms of these two things that I just mentioned, minimizing training loss and validation accuracy? So how effective is the training procedure depends on a couple of things. Okay. Yes, this is there is a question if 30 epochs is standard. No, this is just an example. Okay, it could happen after 5 epochs. Okay, it will not happen always every 30 epochs. Okay, so now how good the model, the training, how effective the training procedure is in terms of these two things depends on the number of things. Okay, so it depends on multiple things, and we must be aware of these things. Okay, when we train a model. So the first thing that depends on is the initialization of the parameters. Okay, so different ways to initialize the parameters, the W's and the betas, will result in different results. Okay, and essentially different models. So initialization is really important, and the poor initialization results in really poor models. Second important thing is the optimization algorithm. So we have been using SGD so far, but there are other algorithms more advanced than SGD, like Adam. Okay, so in many cases, Adam can give significantly better models. Another thing is that we have to select the hyperparameters, and we have seen two important hyperparameters, which is the like batch size and the learning rate. So with poor choices of the learning rate, you can get very, very poor models. Moreover, when we want to avoid overfitting, okay, we can use a technique which is called regularization. Okay, and there are several methods for regularization, and each of these methods may have their own parameters. Okay, so we have to tweak these parameters too. And of course, the network architecture is very important. So how many layers are you going to use in your MLP? what will be the dimensions of the hidden layers, okay? So it's going to be 5, 10, 100, you know, these are things that we have to provide, okay, as a kind of, you know, the people who design the network, okay? So the training architecture will not be covered here, okay? So we will not cover the architecture in this lecture. We will cover all the rest, okay? Now, many of these choices, okay, many of these choices, we can check if they're good or not by taking the training loss, okay? So if you, for example, choose a learning rate, the learning rate is very high, the loss is not going down, the training is completely unstable, then you know you just stop it. Stop the training, change the learning rate. So many of these things can be checked by the training loss. But as I said previously, ultimately, what you want to know is how good your selection of these parameters is by checking the model's accuracy on a separate validation set. So we cannot avoid checking the model's accuracy on a separate validation set, okay, if we want to be sure about the decisions of these parameters. Now, in terms of finding a good architecture, which is something that was asked in the chat, in many cases, people have already found good architectures that we can use. There is a whole area in deep neural networks which is called neural architecture search, and it's about finding optimal architectures. But normally architectures are picked by the people who design these architectures, and they are handcrafted. And the way that you handcraft this is that you, by hand, you change some parameters, also using some sort of intuitive thinking, and then you see the outcome on the validation set, okay? Okay. So the first topic that I want to, so for selecting, before we move on, there's a question. So, well, the activation function, I've already told you that you use the ReLU, okay? So there is not really, so maybe you want to check if your use a ReLU improves a little bit the results, but that's it, okay? There is nothing really to check for the activation function. Is a ReLU. That's the one that works, okay? So the first topic that we will discuss is how to initialize the model parameters. The model parameters are basically the weights and the biases, okay? And if you remember, so far in our examples, we have initialized the weights from a Gaussian distribution with zero mean, okay? So zero mean and a standard deviation which is equal to 0.01, okay? And unfortunately, this kind of choice doesn't always work, okay? So we have to come up with something else, okay? Another thing that I wanted to say is that actually in PyTorch, if you don't specify any initialization, then PyTorch will use a default initialization, which is based on Kaimen-Hess method, okay? It's called Kaiming initialization very often, and that works well for 99.9% of the cases. So if you don't do anything to initialize the parameters or the biases, PyTorch will initialize them automatically, and that works well for almost all cases. Certainly for the cases that you will need for this module. So we will see this method in a few moments. But of course, you can choose other methods to for initialization, and all these methods are in this torch.nn.init package. Okay. So as said, this kind of very basic way, zero mean and standard deviation is 0.01 doesn't work in practice. So we have to find something else. Actually, understanding deeply the initialization process requires a lot of maths. So what we will try to just understand is what we need for a good initialization. So the basic idea of these methods that people invented recently to initialize a neural network. So what's the key idea for a good initialization? So it turns out that a good initialization is one so that the values of the input features and the values of the output features are in the same range. Okay, so you have X goes through H1, then goes to H2, goes to H3, then keep doing this, take the output. So for any layer in this network, okay, any layer will take some input features and produce some output features, right? So H2 here, okay, you have the input features that go into H2, and then you have the output features. Now, the input features, so a good way to initialize the network is so that the input features and the output features will be in the same range, okay? So what does this mean? It means that, if your input features are from -1 to 1, then you want your output features to be that range, -1 to 1, okay? You don't want your output features to be, between -10 and 10, for example. What's a quantity to measure this, the range? Can you tell me? So you want the features to be in the same range. What's a quantity that kind of is related to a range? It's not the difference exactly. So it's the standard deviation, right? So, or the variance. So the variance will tell you if you have a bunch of points, okay. So this is a bunch of points, and then you have, this is the mean value of these points. Then the variance will tell you the range, how far the points are spread. So a large variance will mean that the points are spread quite a lot around the mean value, okay? So this kind of idea of keeping the range similar for input and output features was proposed by for the first time by Cloro and Bengio for initializing the weights of a neural network, and it resulted in a method for initialization which is called Xavier initialization. Xavier is the first name of this guy over here. So the first name of the primary author. It's a very well-known initialization method, and PyTorch implementation is over here. Okay. So how does this work in practice? Okay. So instead of using, let me clear this. It's very simple. So instead of using mean equals 0, So previously we used min equals 0, std equals 0.01. Now you will use min equals 0 and std would be the square root of 2 over n input plus n output. So this formula over here. So n input is the number of input feature dimension, and n output is the number of output feature dimension. So if you remember, for our like a single hidden layer MLP of the previous example, we had we had like our first layer, what were the dimensions? So we were going from 4 features and to 5 features, okay? So the number of inputs is going to be 4 and the number of output features is going to be 5, okay? So then sigma will be a square root to 4 plus 5, okay? So instead of using this value, you're using this value over here, okay? So this is for initializing from a normal distribution. I mean, you can do something similar if you want to initialize from a uniform distribution, okay? So that's how you initialize in a much better way. This is called the Xavier initialization. They are related because the output, each output is a linear combination of all inputs, okay? So in a fully connected layer, each output is gonna be a combination of all inputs. So that's why it's related, okay? Does make sense? So if it's different if you're adding 5 things. So it's different if your input has 4 elements or your input has 100 elements, okay? So the actual output value is directly related to how many inputs do you have, okay? And hence the range. That's the kind of intuitive explanation. Now, this was a great step in terms of initializing neural networks, but there was a problem. So this kind of formula that you see over here, it's not that it's not that the authors, just kind of proposed it, some sort of magical way. They did some calculations. They made some assumptions and they made some calculations and they somehow managed to derive this formula. But to facilitate the calculations, they assumed that in your model, you didn't have activation functions, okay? So you didn't have like a reduce function or sigmoid functions. And so the formula that they derived, it was very good, but it was suboptimal from this perspective. So Kai-Ming He, this guy over here, Kai-Ming He, it's a very famous guy, very famous for training very deep neural networks. Proposed another type of initialization, which is called the He initialization or Kai-Ming initialization, and can be found in this function over here. And basically, what he showed that you can initialize the weights of your network using this formula. So now the standard deviation is the square root of the number of input dimensions, not the number of output dimensions, okay? So this suffices, okay? That's the only difference. Previously, we had plus the number of output dimensions. Now we just have the input dimensions. Okay. Okay. And this is like the default initialization that is used in PyTorch. Okay, I hope this is fairly simple. Now, the second topic that I would like to discuss about is that of regularization. So people have taken machine learning courses in the past, probably are familiar with this topic of regularization, as regularization is like a method of choice for reducing overfitting in machine learning. And many methods that are used for other types of models. So not, deep neural networks, but other methods for initialization, for regularization are also applicable here. So just to remind you here that overfitting is, so overfitting happens when after training at some point the validation error goes up. So the error on a validation set starts increasing while the training error still decreases, right? So obviously you don't want that. So this is called overfitting. So there are several ways of avoiding overfitting, and we will go through them one by one, okay? So all these are kind of ways to avoid overfitting. We will not discuss this, okay? So what's the easiest way to avoid overfitting is the early stopping. So early stopping is basically what I was talking about all this time. We simply stop the training when the error on the validation set starts increasing. Okay, so at the end of each epoch, we measure the validation accuracy, and then there might be an epoch that the error, instead of decreasing, or the accuracy instead of increasing, it starts decreasing, right? So your model, after you train for one more epoch, is less accurate on the validation set. So basically you stop the training, okay? And that's it, okay? And that's the best way, actually, to solve overfitting. Now, another popular regularization method that you may be familiar with is called the weight decay, or L2 regularization. So how does this work? It works as follows. So when we train a neural network, we have to define a loss function, okay? So that was the MSE loss, or the cross entropy loss. So MSE was for regression, cross entropy was for classification. So in addition to this loss function, we also add this term over here, okay, where lambda is a constant that is kind of manually defined, okay? So we have to provide this lambda. So what is this term over here? So this term is the L2 norm of the weights. So this is basically, if I expand this is W transpose W, okay, which is equal to W1 squared plus W2 squared plus WD squared, okay? So this is the extra term that I'm adding to my loss function. So, so what happens is that in addition to the loss function, I want to minimize this term. And if we do that, what happens is that we put a penalty on the very large component of the weight vector. So there might be some weights. So these weights over here can have any values. And there could be that W1 is very big, it's like 100. Then W2 is small, 0.1. W3 is also very big, it's like 50. And then the others are small, okay, 0.2, 0.3. So it might be that, it might turn out that some of the values are very big. Now, if I add this term over here, okay, if I add this penalty, if I minimize this term, in addition to my loss function, what I will put is a penalty on these very large terms, and the penalty will drive them closer to zero, okay? And then that would happen is that all weights will have similar values in a similar range, okay? So why is this good? Is that because otherwise these weights over here would dominate the result, okay? Whereas if we have this, if we apply this penalty, then more or less all weights and features have, let's say, equal contribution, okay? So this is the L2 regularization, which is also called weight decay. Now, there is now in L2 regularization, we use the L2 norm, okay? So this is the L2 norm, but we can also use the L1 norm. So L1 norm is the absolute value of W1 plus the absolute value of W2 plus the absolute value of WD. So instead of taking the square, we just take the absolute value. So this looks similar. I mean, it doesn't look very different, but actually one can show that these two regularizations have very different effects, okay? So the L1 regularization, okay, so if you minimize the L1 norm, what it does is that it leads to models that most weights are zero, okay? So if the weights are zero, then corresponding features will be also zero. So this kind of loss can be used for feature selection, okay? So if our model has a lot of sparse, zero weights, like it's also called sparse weights, then we can identify important features in our model. Okay, so for example, if you remember, you can have lots of features, like have a model that in in some particular layer can have like 100 features. But then you want to be able to say which features are the most important. So if you add this kind of regularization, then it might be that many of the weights will be end up zero. So then you can identify the most dominant features. So this is some sort of from scratch implementation of weight decay. Okay, so this function here implements the L2 norm. Okay, and then this for loop over here basically iterates through all parameters of the layer and applies this penalty. Okay. So, but you don't have to implement this yourself. Okay. So this is some sort of from scratch implementation in PyTorch. This is already implemented, and if you want to use it, you have to provide it as an argument to the SGD function. Okay. So you have to set the weight decay to some value WD. So WD here is the value of this lambda over here. Okay. Okay. And very often this value is, in many cases, 5 times 10 to the minus 4. Okay. So that's a good value for this WD. Okay. So it's already implemented. Any questions? Okay, good. So another popular way to regularize the network is called dropout. So this L2 or L1 regularization, as I said, are like common regularizations for all types of machine learning models. A dropout is specific to a deep neural network. So how does this work? Okay. So the idea is very simple. Okay. When you process some data through your model, then for each layer, you mask out some output features, okay? And this is done completely randomly. So mask out, okay? So what does this mean? It means that you take some features, okay? And then you set them to 0, okay? With some probability, P, okay? With some probability P, I take a feature and I make it 0, okay? Otherwise, the value of the feature is the same, okay? Otherwise, I keep the same value of the feature, but I also have to normalize it with 1 minus P, okay? So that's the dropout regularization. Let's see how this works in practice. Well, with an example, okay? So, for example, here you can see this two-layer MLP that we saw previously, okay? And then here you can see the network after dropping some neurons, okay? So here we drop this neuron, H2, okay, and H5. So we drop them, it means that we set them to 0, okay? And so this is for a specific input, right? So this is for one specific input. Then the second, okay, the second and the fifth neurons are dropped, okay? Now, if I process another input, another image, then, randomly, some other neurons will be dropped. So for a different input sample, different neurons are dropped. And each neuron is dropped with a probability P. Okay. So why is that okay? First of all, do you understand what is this dropout all about? So first of all, I want to know if you understand how it works, what it does. Okay. Now, why it works? It works because what happens is that it prevents neurons from co-adapting to each other, so that each neuron, let's say, can learn to capture a specific concept or feature on its own, without relying too much on the contribution of other neurons, okay? So if you have all neurons active, so here you have, let's say, so in this case, over here, for each example, you have all neurons active. So this is active, 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 okay? And this happens for all training samples, all neurons are active. Then it could be that, each neuron on its own needs the other neurons to produce an outcome, produce a result, okay? Which is not very good, okay? So what you may want to have is each neuron to capture something specific from the data, a specific, let's say, attribute of the data, okay? So maybe this neuron captures something that is related to, let's say, if you are using a network to process faces, this neuron is used to, capture the color of the eyes, or if this neuron is used to capture, second neuron is used to capture the shape of the nose or something like that. Now, if you so this is like a favorable property. You want neurons, to capture different concepts, but this may not happen if all neurons are present all the time. Okay, by doing this random dropping of neurons, you kind of enforce this kind of independence. So that each neuron does not depend on the continuation of the other neurons too much. Okay, so that's kind of some sort of intuitive explanation of dropout. And in turn, if you do that, then you avoid overfitting. Okay. So how would you implement dropout? A typical value for P could be 0.8, 0.5. These are typical values. How can you implement this dropout? If I ask you how to implement a dropout, what would you do? Okay, let me tell you what you do. So let's say you have some features. Okay, so features are stored in this H matrix, right? So what you do is you create a tensor that has the same size as H. Okay, let's call this tensor mask. Okay, so you create a mask with the same size as H. Okay, and then you initialize this. So H here is X. Okay, and you initialize this mask with some values from a uniform distribution. Okay, so each element of the mask would be a number between 0 and 1. Okay, so it could be 0.1, 0.05, 0.9, and so on. And then you compare these values with the dropout rate, this probability P, okay? And if they are greater than this, then you keep the value. So if P is like 0.8, okay, this will become 0, this will become 0, this will become 1, okay? So you create this mask and then you initialize it with random numbers, you apply this threshold over here, okay? And then out of that, you create a binary mask, okay? And this binary mask is used to multiply H, okay? That's what happened here. So you see mask times H or X. And then if you remember, you have to divide also by this 1 minus P, okay? That's how you would implement this dropout, okay? And then the last thing that I want to say is that the dropout layer is used after the nonlinearity in its layer. Okay, that's where we put that dropout. Okay. Also, something that is worth mentioning is that it's like a technicality that after you train the model, the weights need to be multiplied by P. Okay. When you evaluate the model, when you evaluate the model on your validation accuracy, the weights must be multiplied by P to get this working. Now, you don't have to do that yourself. This is already done by PyTorch, but you have to be careful to set your model into eval mode. So if your model is net, then you have to do net.eval. Okay, this will set the mode in evaluation mode. Then you can take this and you can take your model and use it on a validation set. Or here I call the model. Okay. Whereas when you are in the training mode, you do net.train. Okay. So it's good to know that when we train the model, we set it to training mode doing this, whereas we are in eval mode, we set it to eval mode using this. Okay. So the dropout value is decided by hand, and so you just play with some values and you check the overfitting basically. So there will be a value that that will reduce overfitting the most and will result in the most accurate model on the validation set. So that's how you decide the dropout value. But good values are 0.8 or 0.5. Now, yes, none of the neurons are actually dropped. So if you use a very small value for the dropout, this could happen, but it's okay. So even if you are using a high value, let's say 0.8, it could be that none of the neurons is dropped. It will be the case for this for one specific example, training example. For the next example, it will not be like that. It doesn't really matter, okay? Because this probability basically says that 80% of the times the neuron will be dropped, okay? So this is pretty high. You apply this dropout after you complete the network. Is a layer that you're using inside your network, okay? It's already implemented in PyTorch, okay? Well, I want to say something, a layer. Everything in a neural network with PyTorch is a layer, okay? So softmax is a layer, linear layer is a layer, dropout is a layer, okay? So all of these are called layers when you try to implement the neural network, okay? So the dropout layer, which is basically this, I mean, the dropout layer is applying this function, right? Okay, is applied after you put the ReLU, okay? At the output of the ReLU, you have the dropout layer, okay? This is the implementation of the dropout, okay? Is that okay? Other questions? So to use this layer in your own network, you have to define it. You have to define a dropout layer in the constructor, and then once you define the constructor, use self. Okay, so you can do your self dropout equals torch dot and then dot dropout, and then you specify p, 0.8. So you do this in the constructor, and then you apply this in the forward function, okay? So you will do something like out equals self dropout of x, okay? And x will be the output of the ReLU function. It's very simple stuff. Okay, let's move on because I have a few more things. I have a few more things to say. Another way of another type of regularization is data augmentation. So what's the idea behind data augmentation? So if you remember,
we said that we train our network for a large number of epochs. So, and each epoch, we will see a training example once, okay? So in our fashion MNIST data set, we have like a 60,000 images. So for a training epoch, we will see all 60,000 training images, okay? Or 50, something like that. So now, in the first epoch, we will go through all training examples. In the second epoch, we'll go again all through training examples. Now, so that means that from epoch to epoch, we will see exactly the same example, okay? But what we can do instead is, instead of using exactly the same example, we can apply some noise to it, okay? So that every time it is a bit different, okay? So for example, instead of using this image all the time, then I apply some sort of, noise to it. So this is called digeometric augmentation. You see, so I'm not using exactly the same image. I'm using different rotated versions of that image. Also, I'm using scaled versions of the image, right? So this is like a scaled version. So every time the image, it looks like the original image, but there is some, sort of augmentation. So you can also change the color if you want. Okay, color is very popular, rotation is popular, scaling. Also, translation means where the object is located in the image, right? This is also very popular. Or flipping, so flip left, right image. So every time you see a different version of the same image, okay? Sometimes also what you can do is that you can take a patch and set it all 0. Okay, so you can take this patch over here and set it to 0, okay? So if I do that, does this remind you something? So instead of using the original image, I just pick a random patch and make all the values equal to 0. Does this remind you anything? So this is called mask out. Yeah, exactly. It's like a dropout thing, but dropout refers to the features of the network. So dropout refers to the features that are inside the network, whereas this mask out is applied to the input, okay? Yes, all of this is to reduce overfitting. And why is this reducing overfitting? Because it's like expanding our data set, okay? It's like having a more diverse data set. So we have like more training samples. Every time the network does not really see just the same kind of image, but it sees a different type of image. So it can generalize better to, unseen, samples from a validation set, okay? No, it doesn't make the model more inaccurate. It prevents the model from overfitting the training set, okay? Because every time the model will be, during training, every time the model will be required to produce a prediction for a sample that is not exactly the same as it was last time, okay? So it reduces overfitting because of this. And during test time, you don't apply augmentation. So this is applied only for training, okay? Yes, each epoch you will see the same example, but it will have a different type of augmentation, okay? So it will look a little bit different, okay? You can also apply some sort of stochastic random method, but these are not used so much. These are these type of, especially for images, you can also try to apply some sort of Gaussian noise or salt and pepper noise, but these are not really very helpful for this geometric augmentation or color augmentation, flip augmentation. These are the type of noises that are really helpful when we train models for images. Okay. Okay, I hope this is clear. Now, the last thing that I want to talk about is the learning rate. And the learning rate is a very important parameter in terms of training highly accurate networks. And to illustrate this, we will use a simple one-dimensional example where we will use a gradient descent to find the minimum of this function over here. So what's the minimum of this function? So what's the minimum of function f of x equals x squared? Perfect, it's 0. This function looks like this. Sorry, it should pass through 0. Okay, this is x, this is f of x. So the minimum is exactly at 0, right? So we will use gradient descent to find the minimum. And if we use gradient descent with learning rate equal to 0.2, you get, and you start from here. So this is the initial point, okay? Then we must move along this direction, and then we have this step of equal to, so then we get to this point, and then we take another step, we get to this point, this point, this point, and very nicely, you can see that we can reach 0. We discussed a little bit how gradient descent works in the second lecture, if you remember. And we said that when we do this kind of optimization, the gradient tells you the direction to move, but the learning rate tells you how much you're moving in this direction, okay? So now we have chosen a very nice step of equal point of 0.2. You get to the right solution very smoothly, but that's not always the case. So for example, here we show the same kind of process of getting to the minimum value using a much higher learning rate. So 0.9 in this case. So if the learning rate is high, normally you can make big steps, okay? But if the steps are too big, then you might have unnecessary oscillations, okay? So you see here, you oscillate too much, okay? And then, you can still get close to the minimum, okay? But these oscillations are, if the learning rate is too high, are really a big problem close to the optimal solution. So because it oscillates, once you get down here, it will basically oscillate, but it will never reach the minimum, okay? So we want to have a high learning rate to make big steps and train the model faster, okay? Also, if you remember, we said that with a very high learning rate, you might escape some local minima when we optimize the function. It's not the case for this example, but in general, when we train a neural network. But then we have to be careful because once we get close to the optimal solution, then a high learning rate might not be the very good idea. So what is our approach for solving this problem is that we start with a very high learning rate and then we reduce it, okay? So the learning rate is kind of, it does not remain constant for over the course of the training, okay? So for example, what you can do is that you can start from an initial learning rate and then choose learning rate over 2 after, every 50 epochs, okay? So every 50 epochs, you divide the learning rate by 2, okay? What is a good way to, how do you know that you have to reduce it by 2 every 50 epochs? One strategy is to start with a high learning rate and then every epoch, check the accuracy of the validation set, okay? So at some point you will see that, you know, the accuracy doesn't improve, okay? Then it might be the case that it's a good time to reduce the learning rate, okay? Another strategy would be to keep the learning rate constant for t epochs, let's say for every, you know, t epochs, and then reduce it like this. Learning rate new is equal to the old learning rate times 0.99. Okay, so maybe t is like 2 or 3 epochs. Okay, so every 3 epochs, if t equals 3, you apply this formula. Okay, so the new learning rate is equal to the old learning rate times 0.99. So gradually it goes down. Okay, so there are like loads of ways to define your learning rate, to adjust the learning rate, and this is called learning rate scheduler. Okay, so the way that the learning rate is adjusted during the training is called learning rate scheduling, and there is a learning rate scheduler that allows you to do that, and that's also something that the PyTorch can help you do. Okay, so there are multiple ways of doing this business are already implemented in PyTorch. Okay, so just to so in this case the learning rate is 1, it's too high, and it doesn't converge at all, you see. So if your learning rate is too high, it just diverges. Okay, I just wanted to show you this. No, keeping the learning rate low is a bad approach. You should have a large learning rate, so you can increase the learning rate up to the point that your training diverges, like here. Okay, so generally speaking, people are using a high learning rate to train, and then once you check on your validation accuracy, for example, and see that, you know, it doesn't improve, then you can make it smaller. That's a strategy, good strategy for adjusting the learning rate. Okay. And with this slide, I think we're done. So questions, are these hyper also searched through grid search, etc.? So yeah, actually choosing good hyperparameters is something that requires a lot of experience. You can do a grid search, but the grid search might take ages to finish. So what people do is try a few values and then see what they got, and then they, you know, next time they use some other values and so on. So it's kind of try and error procedure. Other questions? Yeah, it's not entirely randomized because you start from some values, and then you check the results. Grid search means that you specify some ranges for your hyperparameters, and you take all possible combinations. Okay, so you say I want to try dropout rate 0.5, 0.6, 0.7. Okay, 0.8. Okay, I want to try learning rate 0.9, 0.8, 0.5. Okay, so you take all types of combinations. Okay, and then you find the best setting. Okay, but obviously you have to try too many things, because you have one hyperparameter here, a second hyperparameter here. Maybe you have the lambda of the weight decay, so you have too many hyperparameters, and the grid search would mean that you have to pick a specific combination of these hyperparameters, train the model, and evaluate it on the test set. So that's the optimal thing to do in terms of finding the best configuration, but it takes a lot of time. So you don't really do that in practice, unless you can train your model very quickly. So if your model, if training the model takes, I don't know, like 1 minute or a couple of minutes, then maybe you can try it. Anything else? Other questions? You can, if there are no other questions, then guys, you can move into the lab and do the lab exercise for today. Thank you, guys. Yes, the next lecture would be only about the assignment, because you're also supposed to have a, I think, first of all, it's very good to take a break, have some time for catch up, but also you're supposed to have a reading week from this year. So like a short break. I think we can introduce the assignment during that break. Okay, so no new material, just the assignment.